Okay, we can get started. Sorry for the delay. It's going to be my mistake. So it's a great pleasure to have Vir to speak today. Vir got his PhD degree in physics from Berkeley and then he did his postdoc at Princeton. After that, he got a faculty position from US University. Very fortunate for us. Before going to the US, we decided to spend half a year here in the US. So we have done many interesting events in the information theoretic aspects and dynamical aspects in quantum mechanical physics, including like complexity, transport, hydrodynamics, and so on. Today, this is something about quantum circuits. Although this is just one topic, because we have done so many other things, I think before he goes away, we should really try to extract as much physics as possible from him. Okay, let's welcome.
Yeah, thank you very much, Gudrun, for the kind introduction and for the opportunity to speak. Okay, so many body physics, as we know it, has changed. Instead of doing things in equilibrium, Hamiltonian time evolution, or whatever, we're doing controllable materials that are far from equilibrium, often far from unitarity. And what this means is that our textbook models of physics don't really work. The Ising model doesn't get you very far in this new setting. And what we need is new versions of the Ising model for these strongly non-equilibrium and often non-unitary dynamics. And I think it's fair to say we're only beginning to chart out the space of possibilities of what can be done here. These systems haven't been around for long enough for us to really have a mature theory, so I think there's still a lot of scope to build the foundational models of this space. And one model which has emerged as a useful starting point independently, actually, in several different subdisciplines are these random unitary circuits. So this is kind of a minimal model of local unitary quantum evolution. You throw away all structure except for just two local unitary gates. And of course, this was quite natural from the physics viewpoint. It's just a universal way to try to probe locality plus randomness. That's how the physicists got there. But interestingly, around the same time, there was a completely independent effort on the CS theory side, because these are somehow native to realize in quantum computers. These are kind of the simplest unstructured dynamics you can do in that setting. And the computer scientists were interested in how hard it is to sample from measurement outcomes of these circuits. As they become higher and higher in depth, they become more random, and it actually becomes harder to sample from. Finally, this culminated in experiments on so-called quantum supremacy, using this idea of hardness of sampling to show that architectures like this are really doing something quantum. So somehow these circuits have emerged as a useful organizing principle, but so far everything's unitary. I haven't talked about the non-unitary dynamics that I said these systems can support. Well, a simple way to introduce non-unitarity that, again, works very cleanly on these devices is by adding measurements. So you take your random local unitary circuit and you intersperse it with local measurements. In this case, interest was spearheaded by physicists who were focused specifically on a phase transition in the system. The so-called measurement-induced phase transition, if you measure sufficiently frequently, you dramatically change the entanglement properties of the late-time state. And what this means is that the corresponding computer science ideas in the random unitary case haven't been developed yet. Actually, people also haven't thought that much about universality within the phases, which was what motivated a lot of the unitary work. So what I'm going to try to do today is give that perspective on how these monitored circuits, actually the phases on either side of the transition, are interesting, because they give us a kind of universality that characterizes circuits of measure. So I'm going to try to build RMT universal model of the volume law phase, then that's going to be the main focus. Okay, so I'm going to start by just presenting a general framework for how to think about the statistical physics of monitored phases, then specifically focus on the volume law phase of these monitored circuits, connect this to integral models as kind of a solvable model for the volume law phase that I'm going to present, and then tie it all together and try to come back to the local case and ask have we learned anything there. So how do we think about self-monitored circuits in general? Well, a crude way to do it is to divide your time evolution up into unitary blocks and measurement blocks. So you have some initial pure state psi, you're just going to hit it with alternate layers of unitaries and measurements. Then we can characterize a given quantum trajectory by the so-called Krauss operators, which are just products of projectors and unitary. Very natural, that's what you might hope dynamics looks like. And then along a given trajectory with some vector of measurement outcomes m, here m just encodes all possible measurement outcomes at all qubits on the flare. The state is given by this. So we take this unnormalized product and then we normalize it. And for a mixed state, so in general, we have many possible measurement outcomes. If we do in quantum mechanics, we need to sum over all of them. And so a long times, the mixed state that results is just a sum over these Krauss operators. So you should think of this as the definition of time evolution when I'm doing circuits like this. I mean that the density matrix is evolving in that way. And anything you want to ask about the circuit, therefore, any observable property of it has to be encoded in this Krauss operator ensemble. So when I talk about the statistical physics of the monitored circuit, I'm going to be specifically the statistical physics of this ensemble of matrices.
So in this class operators, it's always UP, UP, UP. It cannot be UPPP.
Well, it could be, yeah. It's just the way I've set this up is UP,
but if it's UPPP, then the state may just be 0.
Yeah, that's what gives you the different phases. So here by P, I'm actually taking a product of all the different projectors. So if I have another layer of measurements, it would be UPP and so on. And the point is, you want few enough. In one phase, you don't have many P's, and in the other phase, you have many P's.
But does this formalism capture the case where I have UPPP?
Yeah, it does. So we'll get that should become clear. This theory as well. Okay, so yeah.
Sorry. So is it always possible to encode the quantum process into a process?
Yes.
Yes, always for any
modular assumptions on where that process starts from, and so look up CPTP maps. That gives you a general characterization. Okay, so this ensemble contains a huge amount of information. I have possibly some random unitaries in each layer, all these measurement outcomes, generally exponentially many. So we need to boil it down to what's important. And in ordinary Hermitian systems, we look at spectrum. Here we don't have a Hermitian matrix, so we can't diagonalize it. Instead, we use the singular value decomposition. So a way to motivate this is, well, K dagger K is Hermitian, and we can diagonalize that. Yeah, so any K you can split into a singular value decomposition, where in general I'm going to take the singular values to be ordered. And in particular, if K is a random matrix, then B, D, and W are also going to be random matrices. So all of these are random variables that describe ones. Yes, so I'm just going to take my K and rewrite it in terms of the singular value data. And one crucial insight that's emerged from this MIPT literature is that only a small amount of this information is actually important at long times. So while at early times, all of the singular values and all of the singular vectors matter, and late times, only the first few singular values and singular vectors matter. So this is what's called dynamical purification. It's the statement that the long-time behavior of this ensemble can just be characterized in terms of sigma 1 and sigma 2 up to exponentially small. Questions? Okay, so there are two time scales, actually. As Newton pointed out, these sigmas can become 0. And that actually defines a time scale on which all of them become 0. And I'm going to call that the rank collapse time. You may have, some people have called it the hard purification time in the past. It's the point at which you measure enough that the rank of your Kraus operator actually becomes 1. So there's only a single non-zero singular value. This was defined initially, I think, in terms of what's called the Hartley entropy, and there was this famous paper which related that to a percolation transition. You should think of this as the percolation transition happening when I break too many bonds by measuring. It's actually different from the measurement-induced space transition. It's a different transition. So that's one time scale. The other time scale is the purification. And this is the time that it takes for only the first singular value to matter. So it's subtly different from the rank collapse time. Right? With the purification time, you have a lot of these singular values in play, but they're all decaying relative to each other, and in the end, only the largest ones survive. So let me describe that in a bit more detail. There is this ergodic theorem which, because the singular values are decaying, because we have a dissipative process, there is a theorem that guarantees that each one decays exponentially with some rate. And that rate is called the Lyapunov exponent, and it's guaranteed by this ergodic theorem. So informally, you should think of each singular value decaying at some rate lambda n. And then the purification time is a wait until only the first singular value matters. So it's the time scale at which the second singular value becomes exponentially small compared to the first.
So here lambda is negative.
Now?
Is lambda negative?
Yes. Yes. And in order to see a genuine monitored phase of matter, we need at least 2 singular values in place, so we can't have rank collapse. So we need these timescales to be separated. We need more than one singular value, and we need to see purification before the singular values all collapse. So we need this criterion. So the rank collapse time is much longer than the purification.
So is there any relation between the rank collapse time and some of the Lyapunov exponents?
I think no. Well, only the relation given to you by the entropy. So if you're counting non-zero Lyapunov, no, in a word, no. It's they're not related.
Isn't naively, I think it's just roughly, and tau r is roughly 1 over lambda 1. Lambda 1 is the smallest.
Well, yeah, so they're different processes. Yeah, the thing is that all that Lyapunov stop being defined, basically. As soon as the rank collapses, everything except lambda 1 is not defined. So they're genuinely in competition with each other. These two things don't make us.
Yes.
Okay, so I said this gives you universality in the late time dynamics, but let's see that really explicitly. So let me take one of my Krauss operators and write its less singular values just explicitly. Then if I start from an infinite temperature density matrix, maximally mixed state, no structure at all, I go follow any individual trajectory. What this is saying is that at long times, that trajectory is going to be dominated by exactly two vectors. Now, these are random vectors. So at each time, there are only two random vectors in play, but the point is, this is a rank 2 matrix. If you squint, it's not a full rank matrix, it's really only controlled by these two vectors. And the time scale for this second vector to die off is controlled by the sigma 2 divided by sigma 1, which is precisely decaying the purification route. So this is where the purification time comes from, it's this, the decay of this second. Now rank elapses when this second piece suddenly drops to 0 because you've done too many measurements. So they are genuinely different.
Will it also be possible for the rank elapse time diverges in certain settings of inserting by the medicine?
So
Wouldn't the rank elapse time diverge?
we wanted to,
Oh, I see.
yeah. They both diverge, so it's making them keeping that separation of scales on the thing. Okay, so the other, so this is the late time density matrix along any given trajectory. And yeah, there are a few pieces of data. There's this pre-factor sigma 1, this is lambda 1 basically, and that's what ends up in showing the probability of the trajectory. So this gives you the Born probability for being on that trajectory. That formula, there is this ratio of the two leading singular values, which as we've discussed controls this. This is my definition of dynamical purification. So there's a discussion of dynamical purification. In those papers, you can think of it as being defined by the decay of these two singular vectors, values. And finally, the random vector V1 at very late time is going to control any observables or entropies I want to compute from this trajectory. So this is what I meant about universality. So at really late times, beyond the purification time, you just have this vector V1, and now you have a random vector, which is rather like ETH or Berry's conjecture in quantum chaos. Any questions?
So is the rank elapse a generic feature of any sequence of cross?
I think if you place measurements randomly and independently, there's always a risk. So the simplest way it happens is the slow probability event when you measure every single site. Right. So for the local, you actually have to think a bit about how to avoid it. So in the local case, for example, if you only measure, say, the left half of the system, you're fine, because you'll never.
But I guess if I define a generic ensemble of random cross operators, I would not expect rank elapse. It's only because you're measuring.
Yeah, I think it's because we have projected measurements independently. Independent projected measurements. It just happens to be the case for the semi-PC.
And just to ask a more general question, so here you're saying that generically there will only be one dominant eigenvalue, and that's because are we measuring? Is it because we're measuring the local basis? That's why local magnetization basis.
I think it's just this now is a generic property of having a distributed process.
But because if you measure the Born variables, like the instead, then we can get a different transition from a paramagnet to paramagnet. Feels like it would show up in the.
Yeah, it should do. So I think that might give you maybe more dominant singular. Exactly. So yeah, exactly. So it would be reflected. Just a different flavor of universality.
Yes.
Very naive question. Why do we only consider the left singular vectors here?
Just because I felt like if I gave you a more complicated density matrix, the right singular values vectors would show up as well. They're just cancelling out, which is the identity. That's a good question. Okay, so for those of you familiar with the standard MIPT, this discussion might be a bit strange. Let me just relate it to how people usually talk about this stuff. So this percolation model by Skinner, Grumman, and Nen that I mentioned before tells us basically for local 1D measurements, the rank elapsed threshold looks like percolation on a square lattice. And that happens at probability 1/2, and a simple path counting estimate gives you this value for the rank elapsed time. And you can see that in the non-percolating phase, this time scale is infinity, as L goes to infinity, because the rank never collapses. So that gives us percolation threshold P2 star. Everything beyond P2 star is basically you have rank collapse, and therefore you're not really seeing MIPT physics anymore, I would say. So I'm calling that the trivial. What's much more interesting is what happens below P2 star, and then you have this apparently new measurement-induced phase transition that people are interested in that doesn't fit nicely into any kind of existing universality class. And so it's known from mostly numerics, but also from the field theory type arguments Swenway was alluding to earlier, that there are these three regimes of scaling for the purification time. If you measure very little as a volume law phase, when it takes exponentially long to purify, at the transition itself, we seem to have some kind of emergent formal invariance, and then the purification time scales with the system size. And finally, there's this area law phase where the purification time grows much more slowly. It's either constant or logarithmic in L, but either way, it's clearly distinct from exponential or linear. And the numerically determined value of P1 star is around 0. Yeah.
So what is the vertical?
This is, here I'm describing these transitions in terms of timescales. So it's the log of a timescale divided by the system size. And you can see that the purification time is well separated from the rank. Okay, so now I'm going to try to, so it's worth emphasizing there isn't that much analytical understanding of this phase diagram, especially for qubits. So the field theory arguments are valid really in high Hilbert space dimension, while for qubits, it's really not understood analytically. So part of the main goal of this work actually was to make this picture rigorous in at least one setting. So I will not tell you.
Question. So this statement that the rank collapsing time is 1/2p to the L. Is this some model dependent statement or?
Yes, absolutely. So this because the model that these guys considered and Matthew Fisher as well has become very influential because it's basically a square lattice. That's where this 2p, if you had a different geometry, it would have a different population threshold and it would be a
But is it always something 1/something to the power of L?
I would think so.
Any intuition?
Well, okay, so you know that different lattices have different population probabilities. And so what's happening here is it's P over P star to the L. And I suspect that in any lattice that would be the case. That you have an infinite time if you don't percolate and finite time if you percolate.
But is it always is it always the case that this thing can be mapped into some kind of population at all?
I think so. I think that follows by the discussion of at least that specific way of considering monitor phase where you have independent local measurements. I think so. I think that was one of their main results. Yeah, this seems most reasonable. I don't think I have a systematic argument, but given that it works for the square lattice, I would expect it works for it.
But do you think this depends on the dimension?
I think the percolation interpretation would need to be tweaked a bit in higher dimensions, but I don't think it changes.
So if it's in higher dimension, the power is still L, or L squared?
Yeah, it has to. Okay, so this is like making a cut across the system. So in 1D a cut is linear, in 2D a cut would be a plane, so it would be L squared. So we're going to try to capture this kind of dynamical phase diagram analytically, and the idea we're going to use is just throw away the local structure. So this is very natural to do if you're a many-body physicist, and a few people have thought of it before, but I think it's fair to say they didn't take the analysis as far as it could be taken, so that's what we tried to do. So all you do is go from 2 cubic gates to many cubic gates. In fact, random gates on the entire Hilbert space. And at this point, you have a choice. You can, on how you do the measurements, you can measure each qubit independently with probability P, like the usual MIT, or you can measure an exact number of qubits. And actually, it seems really silly, but these are actually different models, and mathematically they behave.
Sorry, the naive folks.
Yeah.
Just mean by unstructured.
Sorry. I just mean I've got rid of spatial locality. So it's really like a L qubit model. Yeah, we wanted to, that's why we call them quantum dots as well. Yeah, so these having got rid of these structure, these models are basically one-dimensional in time. You just have a blob that you're measuring again and again. And what this means is in this case, we can get the rank elapsed time just by thinking about 1D calculation. It's really where the percolation event is measuring every qubit on a row. And the time it takes for that to happen is exactly what you might guess naively. It's just 1 over the probability of it happening. So use it more carefully. It's time scale is 1 over p to the L. However, if you measure a fixed number of qubits per row, you can avoid rank collapse completely, and the rank elapsed time becomes infinite. So this is the difference between the two models. And it's important because it means in one you can really mathematically define the Lyapunovs, and in one. And in fact, this second model is the one that maps to a solvable model in random matrix theory. So I'm going to use SV with a twiddle to describe equivalence of the singular value spectrum. Okay, so let me fix L qubits, let me fix some number of measurements per layer, and then n is the dimension of the Hilbert space, m is the rank of each projector, that is the number of non-zero eigenvalues. So we take any Krauss operator in the ensemble, given these rules. And the point is that because the U's are random on the whole Hilbert space, I can just fix my favorite projector, and then the singular values of K are going to be the same as the singular values with that projector fixed. So if I stare at this, I can rewrite it using the fact that projectors square to themselves in this way. And then at the level of singular values, I basically have a long product of identically distributed matrices that look the same. And it's simplest to take this projector P just to be some number of ones and then some number of zeros, just a square matrix with this form. And then the key point is that all of these R's have the same structure. I'm taking a unitary matrix and I'm conjugating it by this kind of filter, and all that's left is the upper left submatrix, which is m by m. So I reduce this complicated product of complicated Krauss operator just to the singular value spectrum of these matrices, which all have the same form, where I have some R-random submatrix in the upper left corner, and everything else is zero.
The submatrix as an m by m matrix is not unitary.
Exactly, it's not unitary. It's like I took a random unitary and I threw away most of it. So these have been studied by mathematicians actually. They were introduced in 2000 and called truncated unitary matrices. And so now we have a precise statement in this model is that the singular value statistics, the Krauss operation ensemble, is precisely the statistics of products of truncated unitary matrices. So that's somewhere to start from. And these are actually quite well studied. It turns out that, so we try to compute the Lyapunov spectra ourselves, and there is a way to do it, which you can ask me about if you're interested, but it turns out people had done this, and you can actually get the Lyapunov spectrum analytically. It's defined in terms of the digamma function, this psi, and so we have this formula, we can test it. The test is kind of redundant, but you can simulate random matrices on 6 qubits, and you see that this formula works perfectly. So if I average over, if I just run the circuit for a very long time, I can extract predictions for the Lyapunov spectrum, and you see they are in line with the prediction. And in particular, I can get actually an exact formula for the purification time. So down to prefactors, it's just the difference of digamma functions, which turns out to be the difference in inverses exactly. And then you find that it's 1 over 2 to the 1 minus e times tau. So if you measure very little, takes a very long time to purify, and if you measure a lot, purify straight away. So what we've done is we've got the exact purification time in a R-random model, and you can think of this as a solvable model for slow purification in the volume law phase. It's kind of an idealized model of volume law phase where we can really in physics time.
If p is smaller than 1.
Yeah, if p equals 1, then you measure every single. So nothing happens.
I guess because now there's no locality, it would be natural to expect some volume law phase.
Yes, exactly. Somehow the volume law phase was a surprise when it came out. I think from this point of view, it's not so surprising at all.
But I thought at the beginning the surprise was there was locality, and then it might be more surprising.
Yes, but then I can, well, then you can argue that if I can go long enough without measurements, then my unitary part basically looks like a very non-local. So, but you're right, it's more surprising with locality, but here at least is a very simple intuition for why you have exponentially long purification.
So it's more surprising for what, sorry?
Local systems.
The fact that this is a volume of all of these.
Yeah. Okay, so what we've done now is accomplished our goal. Remember, I've presented the MIPT to you like this, just in terms of these two timescales. And at least for these unstructured models, we can get these two timescales exactly. It looks pretty similar. Of course, there's no areal phase anymore. There's no phase transition. There's kind of a trivial MIPT when p equals 1 and you measure everything, but I haven't explored that because we assumed it would be uninteresting. But one thing I find interesting is we needed to patch together two models to get there. So one curve came from one model and one came from the other model, and I suspect if you want to do the left-hand side rigorously, you might need to do the same thing. Any questions on that? So one other thing that you can study to make this connection with random circuit sampling that I started with. You can also look at the probability distribution of Born probabilities. So this is what makes sampling from random unitary circuits hard, is the fact that this distribution is actually difficult to model classically. Now in this case, so for a general monitored circuit, it's true by just the way conditional probabilities are defined that you have a formula like the top line, and you've been doing any machine learning, you'll recognize formulas like that too. And in general, this is pretty complicated, but for our model, which kind of forgets what it's doing at every time step, these conditional probabilities are IID. So they all follow this Porter-Thomas-like distribution. And what this means is we can actually describe the probability distribution of Born probabilities analytically. It's not something you usually think of as being possible to calculate, but here you can, and you can show rigorously it's not log normal at long times. The mean is exactly what you'd expect. It's the probability of just uniformly sampling from all possible measurement outcomes. Whereas its variance here, it's small, well below the purification time, and it's large above the purification time. So this gives us another interpretation of the purification times. It's telling us when we go from narrow to broad distributions of Born probabilities. In other words, it's telling us when trajectories start to look statistically very different from each other. So you can see this here, it's converging to log normality very quickly. And for the black curve, all trajectories look pretty much the same, no matter what you saw in your measurements, whereas by the time you get to this yellow distribution, things are starting to depend on measurement outcomes. There is a broader distribution. Now, finally, you can ask, well, do local systems behave like this? And here are some small system numerics just to show that we're not completely off the mark. There are some vestiges of this kind of behavior are showing up in the local case. And if anyone has access to a cluster and wants to investigate this further, I would be happy to discuss that.
So just to check, so the drift in the log P is controlled by the leading the output exponent, where the spread is by purification time, which is the first and second.
Exactly. And we'd like to, one thing I'd like to understand is how general that is. Can we learn stuff about the local transition with that?
And if you were, if the log normal fit were to deviate from Gaussian, it would happen at the earlier time, at shallow circuit.
Yeah, exactly. So in this example, you can barely see it. That is a deviation from Gaussianity that goes away. Yeah, we don't even expect Gaussianity here, right? So I'm telling you it's a beta distribution. It's only a long time. Yes.
So for these two models, suppose I increase the system size, do I expect more deviation between them or less deviation?
I think less, but it would be good to check that systematically.
Why do you think that?
Because if you have few measures, certainly in the regime with few measurements, I think that so all you need for log normality is really that the layers are not correlated with each other.
But suppose the system size is very small, then there's not much difference between local system and non-local
It's
system.
true. It's true.
Then, and now in the algorithm, when the system size becomes bigger, then the deviation will be bigger.
Yeah, well, actually, I mean, there's already quite a big deviation here, actually, if you look at the x-axis. These settings are meant to copy each other, but actually, the means are already shifted a lot, so.
Yeah, but when I change the system size, then what happens? This is for fixed system size.
Yeah, I don't know. I haven't looked into detail, and it's something I'd like to. I think some of the scaling laws from the non-local case will survive. But yeah, we expect quantitative differences, definitely. Okay, so some takeaways. We have a solvable model for the volume or phase. We found a mapping to random matrix ensembles. I think this is important because it tells you what the universality class here is. If you want to make arguments in the style of ETH or something, then this is telling you that the voluminal phase should be thought of as a product of Gaussian matrices. It predicts the crossover from small fluctuations at times below the purification time to large fluctuations. And finally, we expect some degree of universality, and some of this will be reflected in local models, like the shapes of the distribution I just showed you, even if the fine-grained features are probably going to differ. So point 4, I think, is where more needs to be done. It would be interesting to explore. So now I'm going to change tack a bit.
Can I ask a question?
Yeah, go ahead.
Sorry. You introduced two kinds of tau RC and tau purification. So,
Yes.
yes. I want to know how to distinguish them in standard models. For example, the seminal paper by Grants, they discuss the purification, but I don't know they discuss which purification time.
Yeah, so that's this slide, I think. It's the fact that tau P is generally much smaller than tau C.
As in the purification transition coincides with the transition of tau P, it's correct.
Yes, yeah. Dynamical, everyone's interested in tau P.
But how to derive such
How do
evidence?
How do I what?
Sorry. Why tau RC do not coincide with the volume law and area law transition?
Is the question what's the critical significance of tau RC in the user model?
So, sorry, I cannot hear well. So yeah.
Can you repeat the question?
Yeah. I think there are two possibilities that are the volume law and area law entanglement transition coincides with tau P and the tau P or the tau RC. But you say that the entanglement transition coincides with the transition of the tau P.
Yeah.
But I don't. I want to know how to establish such a statement.
I think for that, I'd refer you to the papers by Michael Gullins and David Hughes, and then the follow-ups, including those authors.
Yeah, thank you.
Okay, so I talked to you about purification times, but as that question revealed, I haven't really talked about the more standard diagnostics such as entropies. So we can actually get things like Renyi entropies of late time trajectories from this model, but only if we neglect the fluctuations of singular values. There is simply a lack of rigorous results on these random matrix ensembles, and so it's, for example, it's known how to compute the mean density of singular values, but not the fluctuations. That's why when we try to get predictions, they're only valid very short terms. So the bottom line is it's hard to compute entropies from the approach we've described so far. So we need to do something different for that. So what we did was try to make an analogy with related discussions of products of random matrices in one-dimensional metals. So this is the so-called Dorokhov-Mello-Pereira-Kumar equation. And the idea is somehow to turn the circuit on its side. Instead of thinking of layers in time, you're now thinking of maybe a 1D disordered conductor, and you have these poorly transmitting layers in space. And the setting on the right-hand side has been studied in quite a lot of detail, and we're going to try to use that intuition. So what that amounts to in the 1D metal setting is a Fokker-Planck equation describing a flow of singular values in space. The only change now is we're going to do this in time. To get a continuous equation in the first place, we need to move away from this projected measurement limit and rank collapse and all of that. So what we do is, just as a mathematical trick, we weaken the measurements. So instead of projected measurements, we now have things that interpolate continuously between weak measurements and the identity. And skipping a lot of details, you can basically define the logarithms of singular values. And for very small values of epsilon, these things satisfy Blanchard-Van dynamics. So it's a stochastic discrete time differential equation. You have some random noise that ultimately comes from random unitarity, plus some interactions that come from level repulsion. This is all standard in the DMPK setting. What we're doing here is adapting it to the monitored circuit setting. And what you find is that if you take the continuous time limit in this case, you get a Fokker-Planck equation for the flow of all of these singular values at once. So there's a similar idea in the work of Witkowski, Hastings, and Harley. We're trying to make an analogy with the closely related Dyson-Brownian motion.
Do they also study quantum dots?
Yes, but they did things slightly differently. Yeah, I don't think they took the analysis as far. They also imposed the Born rule, which we're not actually doing. Okay, but for now, this is the equation describing the flow of singular values of this Krauss ensemble. So let's just study it and see what we learn. Now it looks like a very complicated equation. All we've done is mapped the many-body quantum dynamics to a PDE in 2 to the n variables. It's not very, doesn't seem very helpful, but if you've ever done any work on intricable gases, this is actually very reminiscent of the hyperbolic Calogero-Sutherland model. And so there is a textbook way to solve these equations. by mapping them to imaginary time Schrodinger equations. So there's a well-defined change of variables that you do that takes you basically from Fokker-Planck to Schrodinger with some potential. And the remarkable thing that happens in this case is when you just open the textbook and turn the crank, you find that this interaction potential, which is some nasty free body interaction, ends up becoming a constant. So what this means is you go from this complicated Fokker-Planck to just essentially a non-interacting Schrodinger equation. And the end result is that you can solve the singular value statistics by doing free fermions in imaginary time. It's like diffusion with strange boundary conditions. So this is reminiscent in many ways of Dyson-Brownian motion. There is also work in the DMPK setting which found a solvable case. We thought we were the first people to do this, and then afterwards found that two mathematicians had discovered this in the context of what's called isotropic Brownian motion. So if you like, this is another way to understand the universality class of these circuits. It's this concept of isotropic Brownian motion. Yeah.
So I think the probability starts from the totals. So what you do here is that you map this equation to a system with a specific Hamiltonian.
Yeah.
And so my question is it always possible to do this?
This mapping is always possible. But then the fact that the potential is vanishing is using, okay,
So in the Fokker-Planck equation, P is non-negative.
Yeah.
So here after the mapping, so in the Schrodinger equation generically, the wave function can be complex.
Yeah.
This doesn't matter. Yeah.
So let me describe the solution in a bit more detail. So once you do all this stuff, you find the relationship between P and size given by this, where this wave function now satisfies imaginary time Schrodinger or just a heat equation, except that the boundary conditions are fermionic. So that's the only change. And what this means is that you have to consider something quite strange. It's a Slater determinant of solutions to the heat equation. And this thing is real. So it's a real prefactor and then a real solution that satisfies your boundary conditions. And of course, it has to be real because we need a probability interpretation. And the interpretation of the fermionic statistic here is they're giving you level repulsion. You need something that makes levels repel, and that's what the fermionic statistic actually does. So here's the distribution function of just two singular values, and you can see that there's this correlation hold.
Yeah.
Yeah.
Can you wrap up within 5 minutes?
Yeah, of course. Yeah. We started at okay, so there's, in summary, you get this distribution, which is quite neat because it lets you interpolate between all these different random matrix theory regimes. At very short times, you explicitly recover the GUE, this distribution function, and at very long times, things spread out. If you plot this now as a continuous kind of distribution, you have what we call a semicircle to square crossover, where the singular value statistics go from GUE to something uniform flat. In this 1D gas context, this is a crossover from a Dyson log gas to a 1D Coulomb gas. And this, just a reminder, this is the physics of purification. So this is one other way to understand dynamic purification. Okay, so we did all this because we didn't understand fluctuations in the projected model. At short time, we recover what we expect, this Gullen's-Hughes prediction for the behavior of Renyi entities. But we can also check now, because in this model we can compute fluctuations, and we can check that this prediction is not modified by fluctuations. So we used some classic techniques in this literature, and we found actually the fluctuations scale as T over TP squared. So fluctuations really are small until the purification time. So to summarize, what this model has consistently shown is that fluctuations go from small to large on the scale of the purification time, beyond just the 4 probabilities I described. Okay, so we studied 2 very different models of the volume or phase, and we found some robust conclusions. First, you have this appearance of generic random matrix theory ensembles in the volume or phase. Second, we didn't use the standard toolkit for MIPT, which is why this talk may have seemed a bit unfamiliar in flavor to some of you. I wasn't doing replicas much about entropies or anything, but we could still do things exactly. So maybe there's some mileage in revisiting the MIPT from this more random matrix theory. We found quite generically the purification time captures this crossover from closely to widely spaced singular values. It seems it's not just the first 2 singular values, it's actually a lot of them, a lot of the leading singular values behave this way. And this is why it coincides with the crossover from narrow to broad distributions of itself. So take home, there's a consistent picture emerging here, and it's underpinned by random matrix universals. And then the next step is, of course, to do this all for local systems, area orphans. Very difficult, we'll see. So with that, thank you for listening, and I will be hiring students and postdocs in Houston from next year, so just get in touch.
Thank you. Okay, any questions?
Thanks for the talk. We have a naive question. So for non-time, so if I consider the singular vector of the cross operator, can I consider my state is projecting to the leading singular vector of the cross operator?
Yes.
So I have a question. So do you think there will be a universal behavior of the vector instead of the value?
Absolutely. And so we know that, so for the first model and for this model 2, it really is a random vector. That's kind of the simplest. We know that in local systems, there are corrections to that.
Sorry, but is it an reversible for model 2? It's a Harmonic vector.
I think so. I think it follows just from our analysis. Yeah. Whereas at least the local models, there's a paper from the Vishwanath group, and I think others from, which show that there are corrections to the page curve. So in that case, it can't be fully random. There has to be, but I suspect there is some universal distribution.
Other questions?
So thank you for the talk. So is it possible to analyze the logarithm in entanglement cases? It's possible. So I mean, by logarithm entanglement, you may possibly get some CFT, and from CFT you have much stronger constraint testing. So maybe I think you can get more power.
Do you mean the non-interacting circuits, or do you mean the area law things? Yeah, so I think people have started to apply related ideas in that setting. It's less clear to me how it all works, because there you're doing kind of much lower dimensional ensembles of matrices, but I think they've been applying similar ideas. But it's anytime you have products of random matrices, this kind of universality.
Okay, maybe it's time to finish here. Thank you, everyone, and thank you.